What you see here is a graph of y is equal to x squared, sometimes seen in functional form as f of x is equal to x squared. And it's just your basic parabola. It happens to have a vertex at 0, 0. It has a line of symmetry, a vertical line of symmetry. And basically what that means is that the right half of the parabola is a reflection of the left half of the parabola across that vertical line. Any point along the parabola has a reflection with the same y value and an x value such that the two are equidistant from the line of symmetry. Okay, right now we have this equation 1, which is in vertex form. Looks a little funny, and you'll see why in a minute. Equation 2 is in standard form. And equation 3, which we'll explain later, is the factored form. And this would otherwise really be x times x, or x minus 0 times x minus 0, but the software doesn't do it that way. But we'll see that play out. Okay, so what happens now as we take the vertex and we slide it along the x-axis here? You see that the original parabola remains in place. Our new parabola has a vertex at 4, 0, and that's reflected here in the vertex form by the fact that we now have the equation x minus 4 squared plus 0. And what we have seen before from function transformations is that when we drag something to the right, it is equivalent to reducing the x value by the distance horizontally that we dragged it to the right. And again, we're now saying that instead of x squared being equal to a certain y value, x minus 4 squared is equal to that same y value. Okay, you'll notice also that when we expand our factored form and combine all like terms, we end up with x squared minus 8x plus 16, which is a perfect square trinomial. That shows up in our factored form as x minus 4 squared. And we know that if we were to set this equal to 0, it would give us a solution of x is equal to 4 and x is equal to 4. And that is reflected here in the fact that we have a single x-intercept at x is equal to 4, which also happens to be the vertex. So in other words, anywhere along this x-axis, if the vertex is located, we're going to have a perfect square trinomial. Or at least we can, if we factor out the a value, we can get a perfect square trinomial. We'll look at cases where a is not 1 in a little bit. Okay, as we now slide this vertex up, our vertex form is changing. The x value is staying the same because we're sliding it vertically now. But our y value has gone from 0 up to 3. And notice now that in our standard form, our constant term went from 49 up to 52. So clearly in this form, what this means is that if this value is greater than the value that would make it a perfect square trinomial, then your vertex will be above the x-axis. Similarly, if it's going to be a value below 49 now, we're going to have a vertex below the y-axis. Okay, notice that as we move this below the x-axis, and the parabola now crosses the x-axis, we have the two x-intercepts pop up. They are located at points 5.590, 8.410. Those are just approximations. Let's move this up just a little bit, and now we can see that our parabola crosses at x is equal to 6 and x is equal to 8. Because those are integers, we now can factor this and over the set of integers. And what we're talking about factoring, we're talking about factoring over the set of integers, which is to say that all of our coefficient and constant terms will be integers only. Whether or not a quadratic is factorable gets a little more complicated when a is not equal to 1, but when a is equal to 1, it will only happen when the x-intercepts are both integers. So for example, here, again, not considered factorable. Here, yes, factorable. Down here, factorable again because they're crossing, we have our x-intercepts at 5 and 9. Okay, so let's put this back up here for now. Notice that as we have moved the vertex around, the vertex form has changed in ways that make it clear what the new vertex is. The standard form has changed, and it's a little harder to tell immediately what the value of the vertex is. We'll look at a little bit at how you can determine that later. And notice as well that, again, we don't have a factored form unless we're getting x-intercepts at integer values. Okay, as we change A, things start to change. So when A is now at a value of 2, notice that, or 3 even more dramatically, our parabola has now narrowed. And the reason that it appears to be narrowing is because, in fact, every y value is being increased by a factor of 3, which means that the parabola is being stretched vertically, which makes it appear as though it's being narrowed horizontally. But it's really more accurate to say that we are increasing all the y values. Notice that in the vertex form, the only thing that changes is this a value right here. The value inside the parentheses, the x minus 8, does not change because our vertex did not move, and the 2 did not change because our vertex did not move. And these are the x and y values of our vertex. In the standard form, however, these two coefficients, or the coefficient for the x term and the constant, both changed. And that's because when we expand this, we're now multiplying everything that gets expanded by 3. And so that's going to change everything here. Notice now when we try to find, let's say, a crossing where we have integer x-intercepts, okay, now we have in the factored form, we see that we still have the x minus 7 and the x minus 9, reflecting the two values that would set this equal to 0, but we also have this 3 out here. So in all three of these forms, the vertex form, standard form, factored form, we have the value a. So that's the one thing that's common to all of the three forms. Other than that, the values, as we call them, j and k for the x and y values of the vertex, those really only appear explicitly in the vertex form. These values, the coefficients b and c, only appear explicitly in the standard form, and these values here, x minus 7, x minus 9, we'll call the 7p and the 9q. The p and q only appear explicitly in the factored form. So each of these forms has a different value for us depending on what it is that we're looking for. Okay, notice now with our a value at a positive, the parabola is opening upwards, but as we move this, first of all, to 0, it just becomes a horizontal line, which makes sense because it's just really the line y is equal to 3, because everything else is zeroed out here. And now when a is negative, the parabola opens downwards, and in order for it to cross the x-axis, our vertex would have to be above the x-axis. So here again, now we have standard form, negative x squared plus 16x minus 60. In vertex form, we have the negative 1 here, and then multiplied by the 8 and the x minus 8 squared, representing the x value of the vertex, with 4 added for the y value of the vertex, and then we have our factored form. Okay. One other thing you'll notice here in these numbers is that suppose that we have, let's say, something that looks like this. We'll set a back to 1, and notice that we have 2 additional black dots here, and those represent 2 other points that are of interest to us. The first is the y-intercept, and that is, in other words, when x is equal to 0, what's the value of y? And that's most clearly seen from the standard form, because when these two terms will go to 0 when x is 0, so we're just left with y would be equal to 5. There is a second value here that is of interest to us, which is the y-intercept reflection, and that is the reflection of the y-intercept point across the line of symmetry to the other side of the parabola. So if the distance from the line of symmetry to the y-intercept is 3 horizontal units, then it's going to be 3 horizontal units in the other direction to get to the reflection of the y-intercept. So we have the x value of 0, and then the x value of 6. And so this x value here is just going to always end up being double the x value of the vertex. So these 5 points are 5 points that we can use to plot a graph of a quadratic when we're given the equation and we're not given the graph, and we need to sketch that graph for ourselves.